In 4.2, we're going to take our exponential functions and now progress into looking at our graphs, see what's going on visually, and then also apply some concepts that we've looked at in previous sections. And so just kind of reviewing as we look at exponential functions, because we've gone pretty in depth with some of those equations we were creating, I want to take it back a step and I want to look at some basics. So exponential functions at their very basis, we could write them as this f of x equal to a to the x, where x is any real number. And a is greater than 0, so it's positive, and a cannot be 1 because, funny things happen with 1. And so when you're looking at this little x right here, we have now moved the variable into the exponent, and you've already experienced that in section 1. And so what I want to do is I want to take a slow approach, and I want to look at, let's plug in some values, see what's happening, kind of the mechanics behind it, apply it to the graph, and just make some observations as we go. So let's look at this function, f of x equal to 2 to the x. And so grab your scientific calculator and let's kind of punch and go as we work with this. So if you're looking at 2 to the x and you plug in x to be -3, you get this value. So we have 2, let's write this together, 2 to the -3. Now if you remember your properties of exponents, you can't have negative exponents. So I'm going to put this over 1 and then move it downward. So that gives me 1 over 2 cubed. 1 over 2 cubed is 1/8. And so at -3, I'm at about 1/8. Now I'm going to plug in -2. So this would be 2 to the -2, same conversation. Rules of exponents, if I move it downward, that gives me 1 over 2 squared, which is 1/4. So at -2, it's at 1/4. Then I have 2 to the -1. So that would be 1 over 2, again, just moving that downward, so 1/2. Then I have 2 to the 0. Again, rules of exponents, anything to the 0 power is just 1. And so that would be here at 1. And then I have 2 to the 1st, which is just 2. So 1, 2, starting to see our movement of our function here. 2 squared is equal to 4. So at 2, we're at 4. And then 2 cubed is equal to 8. And so at 3, we're at 8. And so you can see as I connect this curve, we're getting something that looks like this. Now this was not some kind of curve that we covered in previous sections when we were looking at parent functions, because these are kind of unique. We haven't had x to be in our exponent before this. So you can see it's kind of an L shape, kind of a rounded corner. And we can look at it. And let's kind of make some observations from what we saw happening through these functions. And now that we've had this conversation of these exponents, let me just kind of put in those values into our table so we can make some observations. So this gave us 1/8, 1/4, 1/2, 1, 2, 4, 8. And you saw previous in the video how we got these numbers. And so let's make some observations from that. We can see that, first of all of our f of x's are positive. No matter if we were plugging in negatives or zeros, we still only got positive y values. You can see our function is only existing in those top 2 quadrants. Another observation we can see that as x increases, we can see that f of x's are also increasing, but they're increasing faster. Do you notice that our x's were increasing here just by 1 unit? But once we got over here, we're going up by 1, and then 2, and then 4, and then you can imagine what's happening as 2 to the 4th, 2 to the 5th. They're getting bigger and bigger. So that's kind of an interesting observation. Our last observation we can note is that as x is decreasing, you can see that f of x is decreasing. And so if I'm coming this direction, you can see my x's are going down, my values are going down, and they are approaching 0. It's kind of an interesting take there. And we're going to kind of put all these things together, but I want to make some observations, looking at the tables and looking at the graph. Now I also want to consider, what if we added in a little negative here? Because we've already noticed that f of x's are all positive. So let's modify our equation a little bit and see if something else surfaces. And so if I plug in an x, a negative right there, when I go to plug in, I'm plugging in 2 to the negative something. So when I plug that -3 into here, you can see negative and negative would make a positive. So we're looking at the value of 8. So at -3, we're actually at 8. And then again, I'm doing 2 raised to the negative something. Plug that into here. That's -2. So it gives me 2 squared, which is 4. So 2 squared, which is 4. Then I have 2 to the -1, which is 2 to the first, which is just 2. We're starting to see a curve here. 2 to the -0, that's just 1. 2 to the -1, we've had that conversation, that's 1/2. Then we get 1/4, and then we get 1/8. Again, it's almost like we just kind of flip-flopped what we were doing up here. And so then we get a graph something like this. And so it's kind of interesting here that when I'm looking at it and I applied this tiny little negative right there in the exponent, I still only got the same observation before of our f of x's are positive. But we just have now caused just a reflection to happen in here. So I wanted to really look at this and kind of wave my hands at this, look at tables and graphs, but let's put all these characteristics together. So considering our two functions, I'm just going to consider y equals a to the x. We saw that looks something like this when you're looking on, it's not a very good example there. If you're looking at your xy axis, we had a graph that looks something like this. When you're looking at your xy axis, we had a graph that looks something like this. So let's make some general observation of just a to the x or a to the -x, not a 2 there. You'll notice that our possibilities of domain was all real numbers. And so let's note that as you can make an R with a double stem. That's your all real numbers. There was no x's we didn't use. We have negatives, we have positives, we have 0. So both of these are all real numbers. When we get to range, if you consider this, we've already stated they both existed in the top 2 quadrants. No matter what we did, even in plugging 0, we never got an output of 0. So this is going to be a range from 0 to infinity, keeping them all positive. And we made that observation. You'll notice on both your graphs that we had a y-intercept of 0, 1. And that was true whether we had that negative or not. When you look at this graph here, and you're looking at, is it increasing or decreasing, and talking about the places it does, this is increasing the entire way. And then applying that little negative, this one is decreasing the entire way. And then let's talk about what kind of function it is. You can see that if I were looking at this function, that I could draw a horizontal line, a vertical line anywhere on here. So it would be a function. Same is true here. Got ahead of myself there. And then if I look at it and I draw horizontal lines, you can see it's also going to pass these horizontal line tests. And so what type of function are these? Both of these are one-to-one functions. And so that's important to note as we move forward into this chapter and this section, be having it that it's a function and that it's one-to-one. We've already learned that's going to help us in creating our inverse functions, and we're going to see how inverses and exponentials really aid us in solving. Now that we have an idea of domain and range and intercepts and increasing, decreasing, and these function characteristics, let's consider one of the other concepts we've already covered, and let's look at transformations. Now, you already know the basics of transformations. When you have this plus or minus c on the outside here, that's going to be your up and down movement. We learned that when we have plus or minus c in the inside here, this was our left to right. And then we learned that when we have these negatives on the inside and outside, these were going to be dealing with our reflections. But now that we have moved our negative sign, now that we moved our variable up into the exponent, let's do an example of what that's going to look like. So recapping, with the plus or minus c, we learned that it's going to move it up or down. If it was positive, it moved up. If it was negative, it moved down. No big deal. That was pretty straightforward. But in these functions, it's going to look something like f of x equal to 2 to the x plus 1. And so this plus 1 on the outside here would mean that we went up 1 unit. Now, we learned that on the inside, that was moving it left and right. And so this is going to be left and right, but it was the opposite of what we thought. So really positive was going to move us to the left. Negative was going to move it to the right. So with these exponential functions, this is going to look something like f of x equal to 2 to the x plus 1. You're going to have it way up up here, and then a little exponent. And so this is going to signify that we are moving 1 unit. Remember, it's the opposite of what you think. And so this is going to be to the left. Then let's look at what these reflections look like. Now we learned that when we have a negative outside the function, that was a reflection across your x-axis. We learned that when we have it on the inside, that was a reflection across our y-axis. So let's write that. So that would be reflection on your y-axis. And we've already kind of seen one of these reflections as we're working through it in that previous example. This one over the y-axis, we saw that previously up here. Let's look at that graph. You can see that the red and blue are reflected over their y-axis. And we saw that just by adding that negative right here. So down here in this one, you can see that adding that negative right there, an example of that would be y equal 2 to the negative x. So you're going to see that negative up here in the exponent. So if you have a negative out front right here, that's going to be a reflection on your x-axis. Now, one of the other things I want to expose you to in looking at exponential functions, and we've already looked at this when we were doing compounded interest continuously, was the natural base e. We didn't really talk about it specifically, but if you were to type in your calculator e, it's automatically going to put the exponent up. So if we did this to the first power, this would be 2.718, etc. This kind of fits into the category like pi does, where it is a symbol that represents an exact number. And so that's why it has its special button. And we're going to see some of the ways it's going to help us in the future. But you can see that if I had y equals e to the x, that is an exponential function as well. You can see that its graph is beginning to look like the graphs that we've already experienced. And so if we're taking this all together, I want to do one more thing before we end this lecture. I want to look at how can we look at beginning to work through and solve things, right? Because if you have to think about math class, one of the big ideas that we do is solving for x. And you've been doing that in previous sections to very many extents here. And so let's look at this property here that's going to help us in solving for this x. And it's just one of the ways we're going to do it. It's called the one-to-one property. And what the one-to-one property says is if I have two exponentials such as a to the x equal to a to the y, that if they are the same bases right here, same bases of a and a, well, if they are set equal to each other, then we can assume that we can just set the little exponents equal to each other, and that would be true. So this one-to-one property is going to be really nice, and where your legwork's going to incur is in the fact of changing both sides of your exponentials into the same bases. And so I just want to emphasize here that this is a matter of when you have the same base, which this a and this a, that means that is the base when I'm referring to that. These x's and y's, those are your exponents. And so let me show you how that's going to work out. I have 3 to the x plus 1 equal to 27. In order to solve this, I've got to somehow pull that x out of the exponent. So I'm going to do that by converting these into the same bases, so then I can just set the exponents equal. So I have 3 to the x plus 1 equal to 27. So I'm going to grab my calculator, and in my calculator I'm going to type 3 to the first. Well, that gives me 3. 3 squared, well, that gives me 9. 3 cubed, that gives me 27. So I'm going to substitute in that 3 cubed over here. Now, you do not have to be an expert on all the exponents of 3, but just grab your scientific calculator and start working with those powers. You can see, as we've already talked about, they grow very fast on the outputs, and so you can get to that 27 quickly. Now that I have them as both a base 3, I can come over here and say, okay, let me set these exponents equal and solve that. And so I'm going to say x plus 1 equal to 3. Easy solving. X gives me 2. And I'm done. Now, with some of these numbers, I can see how you would take a logical approach and you would start looking at it and go, you know what, I just kind of played with numbers and I got there. But just know, I'm showing you these examples on numbers you can understand, so you can understand that, yes, 3 cubed is 27. Because we're going to get to the point where you can't just stare at the numbers and think, okay, I could have figured that out without it. It's a matter of, okay, here's my process, and I know it works because I've seen it work with this example. So let me apply that process somewhere else. So make sure you're always showing all steps. In order to receive full credit for a problem like this, I would want to see this step and then solving from there. I was just showing you this step of how I would work it with my calculator and get to that 27. So let's work this one. This one's a little bit more difficult. I have 2 more examples here. Let's look at 1 to the 1/2. You're like, well, teacher, those are not the same basis. Well, let's consider our rules of exponents. Isn't 1/2 the same thing as 1/2? And we say it to the first power when it doesn't have an exponent. So by rules of exponents, if I move this up to the top, it becomes a negative exponent. And so now I have this as a large 2. Rules of exponent state that power to power you can multiply, so that would be 2 to the negative x. Now all this was equal to 8. And so now let's work with our 8. I need some power of 2 that would give me 8. So in my calculator, I say 2 to the first. That's 2. 2 squared, 4. 2 cubed gives me 8. So I'm going to use that substitution right here to change this into a base 2. So it would be 2 to the negative x is equal to 2 cubed. And then now I have the same basis, so I can set these exponents equal. So that gives me negative x equal to 3, and then solve for x. So x is equal to, divide that, negative 3. So I did an integer, I did a fraction. Now let's work with that base e. Now e is really nice, and we're going to pull up some previous skills that we've already learned. Because I already have e as both the bases, with this one I don't have to do any converting. I can just set the exponents equal. So I say x squared plus 12 is equal to 7x. And then I can solve for x from there. Well, that's a quadratic. Let's go back to square one. How to solve quadratics. I get them all over to one side and get it in standard form. It gives me x squared minus 7x plus 12 equal to 0. And then I'm going to factor it. You can't forget all those factoring skills, x and x. My signs are going to be the same, both negative. And then I think what will multiply to give me 12 and add to give me 7, that would be 3 and 4. And then I solve from there. So you can't forget all your solving that you did in chapter 3, because you're still going to have to pull those skills out here. Everything we do is going to build. So make sure you're understanding those concepts. Even after an exam, you're seeking help to reaffirm that good foundation. So I hope this helps as you work through this section. Please contact me by Canvas messaging if you have any questions.